We are now ready for problem 6 on the test review. In a minute, I'll show you problem 6. It's like a story problem. But 6 and 7 are the kinds of problems are called related rates. The key word here is rate. The rate has to do with something that's changing as time goes on. Things are changing with time. So what's going to happen is these related rate problems are all the same. At some point, you're usually given some kind of equation. And what we're going to do is we're going to take the derivative of that equation, but we're going to take the derivative with respect to time. Initially, time is not even a part of the equation. You may have 2 or 3 or 4 different variables. So each time when we take the derivative of the equation, each of those variables, we have to think of implicit differentiation. In other words, we're going to have a bunch of dt's in the equation. Easiest thing is, I think, just to go ahead and do an example and then talk about what we're doing. But related rates, the whole idea is now we're talking about things changing with time. That's what rate means. The rate of something growing. The rate of something shrinking, the rate at which units are being produced, the rate at which money is being spent. It all has to do with things changing in time. So for instance, let me just throw up here problem number 6. Let's read it and talk about it. A floating cap of sea ice has been shrinking since 1980. The ice cap always shrinks in the summer and grows in winter. Average minimum size of the ice cap in square miles can be approximated by A equals pi r squared. So in other words, this must be sort of like it must be like a cone, and what they do, they measure the area, must be the area of the bottom of the ice cap, maybe the area that's sitting on the water. Because this actually is the equation for the area of a circle. So the ice cap must the bottom of it must be like a circle. So in 2013, the radius of the ice cap was approximately 775 miles and is shrinking at a rate of approximately 4.9 miles per year. How fast was the area changing at that time? So what they do is they look at a specific point in time, the year 2013. They tell us at that point in time what the radius is of this ice cap, and then they tell us how fast the rate that the radius is shrinking, or it's just getting smaller, and then they say, therefore, at this point in time, how was the area changing? So let me just write down sort of the information they were given. First, the key thing is to write down the equation So A is like the area of the bottom of the ice cap, and it probably looks like a circle. So there's the radius. The area is how much room that bottom of that ice cap takes up. So R is radius. Pi is a number, right? Approximately 3.14. So in a sense, you have two variables. We have A, the area, R, the radius, then this pi is just a number. So what's going to happen is, since things are changing, we are now going to take the derivative of both sides of this equation with respect to time. So it's almost like we're taking this equation for area, and now we're going to look at it as it changes. And the way we're going to do that is we're going to take the derivative of this whole equation with respect to time. So my two variables here, so it's almost like I'm going to take the derivative of A, which is just 1, but because A is not t, we end up with the a dt. Now pi is just a constant, so it comes out. Now the derivative of r squared with respect to t, once again this is like implicit differentiation, since the variable is different than what I'm taking it with respect to. So r squared becomes 2r, but then you have to add on the dr dt. And that's the key to these related rate problems. Almost always they're going to give you an equation, or the equation is something you can easily figure out. And then what you're going to do is you're going to take the derivative of both sides with respect to time, and in a sense you're turning the equation into a rate equation. In other words, how is it changing with time? Now ultimately, here's what they tell us in our problem. Here's the information they gave us. They're looking at a specific point in time, 2013, and they said the radius of the ice cap is 775 miles. And at this point in time, the radius was shrinking. The radius shrinking means how is it changing with respect to time, which is what dr dt is. And they say it's 4.9 miles per year, but remember, I'm going to call this negative 4.9 miles per year because it's decreasing, so the rate or the derivative would be negative, which means as time goes on, basically the radius is getting smaller and smaller. And then they say at this point in time, with this specific information, how is the area changing? Turns out we have this equation. We've already solved it for dA dt. Pi is a number, it's a constant. We've got 2 here. We're given the r, and we're given dr dt. So in this case, it's just a matter of plugging everything in. So r is 775 miles. Dr dt is negative 4.9. Now I've got my calculator. My calculator has a pi key on it, so I hit the pi key. Times 2 times 775 times negative 4.9. I'm just going to round it to the nearest digit because it's a pretty big number, negative 23,860 square miles per year. So according to these calculations and these numbers, the ice cap, the area of the ice cap is shrinking at this rate. All right. Not too difficult to do that problem. If we go to the next one, our second related rate problem, number 7. Let me just read it. When expanding without gaining or losing heat, the pressure P and volume V of a sample of argon gas are related by the formula PV to the 5/3 equals K, where K is a constant. Suppose the volume of the sample is increasing at a rate of 0.4 liters per second. How quickly is the pressure decreasing when the volume is 2.7 liters and the pressure is 80 kPa? I believe that's kilopascals. So this is like a chemistry or a physics problem. Now the good thing is you don't really have to sort of understand what's going on here, because they give us an equation and then they give us some information. So once we write all this down, hopefully this will make sense. But the key is, what do they ask for? How quickly is the pressure decreasing? They're talking about the pressure is changing over time, and that's what we're asking about. So this is a related rate problem. It involves time, how things are changing. So once again, let's start with just writing down the equation. So P, which is pressure, and V, which is volume. Of course, the volume is to the 5/3 power, equals K. Now K is a constant. So it's like a number. Could be 5, could be 10, could be minus 15. We don't really care. Now to turn this in to a related rate problem, we have to take the derivative with respect to time of both sides of the equation. Now P and V are both variables. Now neither of them are the same as the variable that we are taking the derivative with respect to, because it's time. But we're still going to have to apply the product rule to the left-hand side. So I'll write P. Now the derivative of V to the 5/3, well, the 5/3 comes down, and then we subtract 1, which leaves V to the 2/3. But since V and the T down here are different, we have to also have the dV dt. So that's the first half of the product rule. Second half, I just write V to the 5/3 and then take the derivative of P. Derivative of P is just 1. However, since P is different than T, we now have dP dt. And now the right-hand side, when you take the derivative of a constant, like what happens when you take the derivative of a number? It just goes to 0, right? So the right-hand side is 0. Now let's figure out what information they've given us and what we're trying to solve for, and then we can determine how we want to rearrange this equation. So they say, suppose the volume of the sample is increasing at a rate of 4 liters per minute. The volume increasing. The volume increasing, that means dV dt, and they say it's 0.4 liters per second. How quickly is the pressure decreasing? So really it looks like they're asking us about how the pressure is changing. How quickly is the pressure decreasing when the volume is 2.7 liters and the pressure is 80 kilopascals. So if I look at my equation, I have P and V dV dt dP dt. They give us dV dt. I'm looking for dP dt. They give us V, and they give us P. So actually I have everything in this equation except for dP dt, which is what I'm trying to solve for. So let's get dP dt by itself. I'm going to take this whole first term and subtract it to move it to the other side. So the right hand side is negative 5/3 P times V to the third terms times dV dt. Now if I'm going to solve for dP dt, I'm going to divide both sides by V to the 5/3. So negative 5/3 PV to the 2/3 times dV dt. I'm going to write it right here, over V to the 5/3. Sort of messy, doesn't really that bad. And actually, I think it's going to make it simpler. I'm going to go and simplify because I've got V to the 2/3 or V to the 5/3. If you remember, some of your exponent rules, you have the same base. You simply take the top exponent and you subtract the bottom exponent. That ends up being V to the -1, which basically is 1 over V. So this thing reduces down negative 5/3 P over V times dV dt. And now they've given me what each of these are equal to. So I can plug them in. The pressure, I said, is 80 kPa. They said the volume is 2.7 liters. And then how is the volume changing with respect to time? It's 0.4, and it's increasing. Now once again, if I could grab my calculator. So if I go across the top, negative 5 times 80 times 0.4 divided by 3 divided by 2.7, negative 19.75, the liters cancel. So negative 19.75 kilopascals per second. All right, once again, hopefully, after having done a couple of these related to rate problems, you'll see not too difficult. Basically, you just, whatever formula or equation you're given, if you take the derivative of both sides with respect to time, and then you go see what they've given you, and usually at that point you're ready to solve it. All right, let me stop this video here, and we'll start a new one as we start with problem 8.